third segment of Chapter 9. We've been talking about bonding and Vesper, polarity, polar molecules, and then we just brought up two new bonding theories, which was hybrid orbitals and MO, molecular orbitals. And so we had started down the path of hybrid orbitals, and so we went over the potentials here where we can have an sp hybrid, an sp2 hybrid, sp3 hybrid, sp3d hybrid, sp3d2 hybrid. Now again, when you count up your orbitals here, we have two orbitals, which means one bond, right? Three orbitals, now we have three atoms involved, 4, 4, 5, 5, and these are also your bonding domains, right? So, well, we have two things combined here. That's two bonding domains, three bonding domains, 4, 5, 6 bonding domains. Next thing we want to do is start to look at some of the molecules that will fit into this. So the bonding in BCl3, for instance, each one has an overlap of each half-filled 3p orbital on the chlorine with each half-filled sp2 hybrid on the boron. So the boron then is going to be an sp2 hybrid. Now, how do we get to the sp2 hybrid? Well, what we're going to do is we have 3 electrons in the boron, and if you look at it, it's going to be s2, and of course p would have 1. But we can't bond this way, right? If this is paired up, so what we're going to do is we're going to kick one of those electrons over to either the px or the py, and so now we're going to have 1 electron in the s, 1 in px, and 1 in py, and that's going to give me my sp2 hybrid orbital right there. And of course that means I'm going to have 3 of them, and so here they are, sp2 here, sp2 there, and sp2 there. Okay, so then we get 1 electron in each one of those orbitals, and then of course 1 electron from each of the p orbitals in the chlorine, and so there we're going to see that we're going to fill our sp2 hybrid orbitals. So we're going to form 3 equivalent bonds. It should have a triangular planar shape, which means we should expect it to have a 120-degree bond angle. All right, let's apply this to methane, CH4. So the overlap of each half-filled 1s orbital on hydrogen with each half-filled sp3 hybrid on carbon. So our carbon is going to be an sp3 hybrid. It's a tetrahedral. So it's going to have 4 orbitals involved, 1s and then 3 p's. So 1 electron will come from the carbon into each one of those hybrid orbitals, and 1 electron from each of the hydrogens. That's going to combine to give us 4 filled sp3 orbitals. So we're going to form 4 equivalent bonds, and it's going to end up with a tetrahedral geometry, giving us that 109.5. So hybrid orbitals then, we have 2 sp hybrids, 180-degree angle, 3 sp2, that's going to give us our 120, and then 4 sp3s gives us our tetrahedral. So what is the hybridization of oxygen and OCl2? Is it sp, sp3, sp2, or no hybridization? So now again, if we think about domains and electrons in general, we know that oxygen has 6 valence electrons. Chlorines each have 7. It's going to be 14 for a total of 20 electrons. And of course, hopefully, if you think of oxygen as being a tetrahedron, right, from the basic, just 4 bonding domains, you should arrive at sp3 hybridization. All right, what is the hybridization of the carbon atom and carbon disulfide? Carbon disulfide. Now this one might be a little tricky. We're going to think carbon should be sp3 because it has 4. It's going to form a tetrahedral. But is it? So carbon disulfide, CS2. So hopefully you've worked through it. You came out with sp. If not, here we go. If I draw out the molecule, I have carbon as the central atom, 2 double bonds, 1 to each sulfur. Sulfur then has the 2 lone pairs. Now remember, whenever we're talking about hybridization, we're talking about the central atom. So what is the hybridization about the carbon? Well, the carbon is only using 2 bonding domains. Remember, just because it's a double bond, that doesn't matter. It's a domain. It's a single domain. So if I only have 2 domains, that means I only need 2 orbitals. The 2 orbitals then must be in sp, and it must be hybridized. So we have 2 electron domains. That means a 180-degree bond angle, and that means we have an sp hybrid orbital. All right, the next thing we want to look at is conformations. The CC single bond has a free rotation around the carbon bond. And so what we're saying here is we have the single bond here. We can rotate the CH3 in a counterclockwise or clockwise direction, right? So it can rotate about that axis right there. The conformations then would show us that maybe we have 1 hydrogen up on that side, 2 hydrogens up on the other side, or both of them could be hydrogen up, a single hydrogen going up, okay? So if I look at pentane then, there's a bunch of different conformations we can take a look at. So here you can see we have a zigzag by each carbon. Here we have a down, over, down conformation. Here we have an up, over, down, over conformation, right? So what's going to happen here is we want to try to get the single hydrogen to meld in between the 2, right? That's the best way. That's going to give you your best conformation. Expanded octet hybridization when the central atom has more than an octet. If there are more than 4 equivalent bonds on a central atom, then we must add the d orbitals to make sure we have the hybrid orbitals figured out. Why? Well, again, the s and the p means that 4 equivalent orbitals, the most, means you can have 4 bonds, right? So only atoms in the 3rd row of the periodic table and below can exceed the octet. We saw that before when we were drawing out structures. Same is going to be true here. You have to have that d orbital so that you can use it to backfill to expand beyond 8 electrons. 1 d orbital is added for each pair of electrons in excess of your standard octet. So our expanded octet hybrid orbitals would give us 5, which we saw before is the bipyramid, right? So trigonal bipyramidal. So here we have 5. The orbitals that we'll use will be the sp3 and then the d we'll add in. And then of course the octahedral for the 6 domains would be s and then 3 p's and then 2 more d's, so sp3d2. Hybridization of molecules that have lone pair electrons. So if you work through the hybridization here, we get sp3 tetrahedral geometry. That gives us 109.5. If we throw in a lone pair, we can see that, remember, that lone pair wants to take up, it's going to balloon out, it's going to force the other bonds to get tighter. That angle actually drops down to 107 for ammonia, and for water, we see it drop down to 104.5. Now we have 2 of those lone pair balloons on the back of that, pushing those 2 hydrogens in close to each other. The angles then suggest that NH3 and H2O both use sp3 hybrid orbitals for bonding, because we still have the 4 domains. Not all hybrid orbitals used for bonding electrons, so lone pairs can occupy hybrid orbitals. The lone pairs must always be counted to determine the geometry. Okay, so you can't excuse the lone pairs to come up with that final geometry, but remember, we're using them for the basic shape. The hybridization in the molecules that have lone pair electrons, for instance, if we're looking at ammonia. So here we have 2 s electrons, 2 p electrons, or 3 p electrons. When we hybridize, we're going to use an sp3 piece, but 2 of those electrons are going to be the lone pair, right? So we have the lone pair electrons. We're still going to hybridize it out to give that characteristic of that tetrahedral, okay? But one of those hybridized orbitals will contain both of the 2s electrons. Okay, so again, when we hybridize this, it'll still be sp3 hybridized, but the 2 electrons that were in the 2s will take up one of the hybridized orbitals. All right, so for the species ClF2 plus, determine the following: the electron domain geometry and the molecular geometry. So pause it here for a second, let you work this out. Hopefully you came up with C, tetrahedral, and bent. And again, if we have the Cl, we have F2, and then we have a plus charge on this whole thing. So remember, we're going to have 7 plus 14 is going to give us 21. Then we're going to lose 1, that's 20 electrons altogether. We're going to have 8 in this one, 8 in that one, so that's going to give us a total of 16, which means we have 4 electrons on the chlorine. That's how we're going to get our tetrahedral, and of course, since we have the 2 lone pairs, it's going to be bent. For the species ClF2, determine the following: hybridization around the central atom and its polarity. All right, well, we just determined it was a tetrahedral, so for its hybridization, we know it's going to be sp3, and then is it going to be sp3 polar or sp3 nonpolar? And when I look at the potential answers here, it's either going to be A or C. Not seeing any difference there. I have a feeling one of these was supposed to be sp2 polar, maybe, to kind of throw you off, not tell you that you had a 50% chance of getting that right if you picked that one. All right, anyway, we know it's going to be a tetrahedral, so that's where we get the sp3. And of course, since we have that lone pair, then we have the fluorines pulling away from each other. That part cancels out in the horizontal, but like we saw before, the vertical, we would have an overall moment going through the chlorine. All right, for the species XeF4O, determine the following: electron domain geometry and its molecular geometry. So again, you have to count up your electrons and figure out how many electron domains are on the Xe. So if we put Xe in the center, we know that's got 8, fluorine 28, so 8 plus 28 is 34, plus 6 gives us 40. Draw single bonds to everybody. So this would be 8, 16, 24, 32. And then if we put that as a single bond, that'll give us 40. How many are we supposed to have here? So we had 8 plus 28 plus 6 gives us 42, which means we have to have 2 about the Xe, which gives us our octahedral, and of course, square pyramidal. All right, same molecule, hybridization around the central atom, and of course, is the molecular polarity there. So well, we just figured out it was an octahedral, so we know we're going to need 6 domains. That means it can't be A or C. So it's got to be B or D. And is it polar or non-polar? And of course, we know we got those fluorines pulling in the horizontal, but they'll all cancel each other out. But we also have that oxygen pulling in the vertical. And so that's going to make it polar. All right. Our next topic then is going to be double and triple bonds. So where do the extra electron pairs and the multiple bonds go? They can't go into the hybrid orbitals. That won't make a whole lot of sense. Remember, the VSEPR, multiple bonds have no effect on geometry. So why didn't they affect the geometry? Well, we had two types of bond result from the orbital overlap. Well, we can have a sigma bond, which is going to account for our first bond, and then we're going to have what we call a pi bond. And this is going to account for second and third bonds. So let's take a look at sigma bonds. Sigma bonds are going to be a head-on overlap of your orbitals. Okay, so if we have two s orbitals, they don't have any options here. They're going to overlap what we call head-to-head. And if you flash back into the last segment, you'll remember I talked about this head-to-head. They're going to bond head-to-head. What we're saying there is that they're going to go head-on. Okay, so if I think about that orbital as being three-dimensional, sort of a balloon, there's a couple of different ways I can approach the balloon. I can approach it head-on, which would be like the top of the balloon, or I can approach from the side and get sort of the side view of the balloon. Head-to-head simply means we're going to have a sigma bond. So sigma bonds always bond to that big part of the lobe head-on. Okay? So concentrate the electron density most heavily between the two nuclei of the atoms. Makes sense, right? So the sigma bond, they want to feel the effect of both nuclei to the best that they can. So that's going to be a head-to-head interaction. Whether I'm looking at, an s orbital, a p orbital, or some hybridized orbital, doesn't matter. They're going to lie along the imaginary line that's joining the two nuclei. So if I think of point X and point Y, and I draw a line, we're going to get a head-on overlap between the two, right? Always between the two. It doesn't matter what type of orbitals we're dealing with. So whether it's S and S, P and P, or SP and SP. Now your pi bond is going to approach from the side. It's a sideways overlap of that unhybridized p orbital. Unhybridized p orbital. So the electron density divided into two regions. So now I draw my straight line, but now the interaction is happening outside of that line. Okay, so it's not going to be head-to-head, it's going to be side-to-side. It's going to lie on opposite sides of your imaginary connecting line. The electron density above and below is what's going to generate your pi bond. So it's going to be above and below the sigma bond. No electron density along the sigma bond axis. The pi bond consists of both regions. Both regions equal one pi bond. So pi bonds can never occur alone. We never make a pi bond unless we first have a sigma bond. So the first interaction has to be head-to-head. Then once we have that head-to-head, the remaining orbitals can then interact side-to-side. Okay? So we can form them from unhybridized p orbitals on adjacent atoms after forming the sigma bond. Pi bonds allow atoms to form double and triple bonds, and we're going to look at a couple of those cases. So bonding in ethene, C2H4. Remember, carbon is going to be hybridized. So each carbon is going to be sp2 hybridized. Okay, so it's going to leave one of the p's out. We're going to get the head-to-head based upon that first sigma bond interaction between the two carbons. And now we're going to have the red p orbital that wasn't used in the sp hybridization. sp2 hybridization. Now remember, we did that sp2 hybridization. We got one hydrogen here, and then the carbon-carbon interaction there. That fourth orbital, that p, is now going to be in the xy plane. Well, sorry, we'll call it the xz plane because the xy plane would be the planar sp2 hybridization. So now we're going to say we're in the z plane. So we're actually up and down here. The other carbon has got that same thing going. Well, now what we can do is interact these two p orbitals in a side fashion. The CC double bond is going to be one sigma bond and one pi bond, that p to p side interaction. Okay. Now, some properties of your pi bonds. They can't rotate. So remember, in our sigma bond, that head-to-head interaction, we could rotate about that plane. But for these two to interact, think of it as locking the molecule in. They used to be able to go like this. Now they're locked together because these two are connected, and now they can't. So there's no rotation about that double and triple bond. The pi bond must first be broken before a rotation can occur. Okay? So if we look at the bonding in formaldehyde, the C and the O each have hybridized orbitals. One unhybridized p orbital, which is on the carbon and on the oxygen, is going to interact to form our pi bond. So the oxygen here in our formaldehyde molecule cannot spin around. This is locked in place by that double bond. The unshared pairs of electrons on the oxygen then also have to be in sp2 hybridized orbitals. So an sp2 overlap to form the CO sigma bond. Okay, so if we have a double bond, then we have to have a sigma bond and then one pi bond. In order to do that with carbon, it has to be sp2 hybridized because we have to leave one of the p orbitals out in order to make that p-pi bond. Now, how about acetylene? Now we have our triple bond. Well, the hybridization about each carbon is going to be sp hybridized. So one of those hybrids is going to make the head-to-head between the two carbons, and one of them is going to be the hydrogen-carbon overlap. Now, that means we're leaving two p orbitals out. We now have one that was in that z plane. We also have one that's now going to lie in the xy plane. So we have two unhybridized p orbitals. The CC triple bond then is going to be one sigma bond from that hybridized orbital and two pi bonds, a PXX interaction and a PYY interaction. How about the bonding in nitrogen, N2? Here we're going to see nitrogen is going to be sp hybridized. We're going to have two unhybridized p orbitals, the px and the py in red, just like we saw with the carbon. And now we have the nitrogen-nitrogen triple bond, where we're going to have one sigma bond, the sp-sp hybridized interaction, and two pi bonds, the px and the py. All right, how many sigma and pi bonds are there in this molecule? And what is the hybridization around the carbon atoms? So is it 7, 1, 8, 2, 9, 2, 9, 3, 8, 2. So how many sigma bonds? Remember, every single bond is a sigma bond. So we have 1, 2, 3, 4, 5, 6, 7. Before we can make a pi bond, we have to make a single bond. So there's 8 and 9. Now we have two pi bonds. So right now that means we should be C9, 2, sp2. And that is correct. Now, if I want to figure out the hybridization, well, remember, if I look at this carbon, we'll call this carbon 1. It's got three interactions. 1, 2, and 3. That means I need three orbitals. So that's going to be s and two p's, sp2 hybridized. I can do the same thing for carbon number 2, 3, and 4. So all four of them in this molecule should be sp2 hybridized. How many sigma and pi bonds are there in carbon monoxide? And what is the hybridization of the C and O atoms? All right, so how many sigma and how many pi bonds are in CO, carbon monoxide? Well, we have 4 plus 6 is 10 electrons. So I'm going to draw on a single bond. And if I try to put dots around everybody here, we're going to find out we're way over. All right, so remember we have 10 electrons. Right now we have 2, 4, 6, 8, 10, 12, 14. So I'm going to put these two in and these two in. That's going to give me my triple bond now. Whoops, just messed that up. Erase, erase. I'm tired, sorry. Putting in pairs doesn't help me, right? I want to get rid of the pair and put in single electrons first. That's what I meant to say. So instead of having a pair here, we'll make a double bond. And that way carbon has 8 electrons. Oxygen has 8 electrons. Now we have 2, 4, 6, 8, 10, 12. So we'll do that one more time. We'll get rid of a pair, get rid of a pair. Now we'll make a triple bond. We'll put a lone pair on the carbon, put a lone pair on the oxygen, and now we have 2, 4, 6, 8, 10. All right, so there's our 10 electrons. So there's our molecule. So if this is indeed the correct molecule, where carbon is a -1 and oxygen is a +1, using our formal charges from last chapter, not a very good molecule, but that's the way it's going to work out for now. We can take a look at this. It says we have one single bond, which we know we have to have first. Oh, well, that really is kind of silly, because just based on that, that means the only answer possible would be A, which we are correct. It's A. And 2 pi bonds, and then both would be sp. So, and again, they're showing us we have a triple bond with our lone pairs. So that's exactly what we came up with, right? All right, so I don't like that they didn't give us any other ones here to make us work for that a little bit. So let's work backwards and look at our hybridization. So for carbon, then we knew we were connected to one other thing, which means how many orbitals are we going to need? We're going to have 2 different domains, one for our lone pairs and one for our bond. So that meant we had to be sp hybridized. In order to be sp hybridized for carbon, then we knew we were going to need to use 2 pi bonds. So a couple different ways to work through that. I didn't like it that they only gave us truly one potential. I wish one of these other ones would have been 1 sigma bond as well. All right, so we're going to stop here for segment 3. We'll go into segment 4 and we'll switch gears into molecular orbital theory. So we're going to change just a bit and look at it, the same bonding from a different way, I guess, if you will, a different theory. All right, stay tuned.